Alright, hello. Today we're going to do a little demo on the Zybo Zynq 7000 SoC dev board. Got it right here. And we're going to be running two Baremetal applications simultaneously, one on each ARM core. So each CPU is going to get its own AXI GPIO. And we're going to give it two switches and two LEDs each. And our goal is to have a CPU read the switch values of its AXI GPIO, write it to on-chip memory, and the other CPU will read the switch values and set its LEDs accordingly. And another thing is we're going to use a flag to make sure only one CPU writes to shared memory at a time, because it would be bad if both CPUs were to try and write to the same address at the same time, get like memory corruption, other not fun stuff. So yeah, here's the architecture of what we're going to be doing today. A little backend information: the CPUs have their own private level 1 cache, private peripheral interrupts, memory management unit, private timers, and watchdogs. And they share a level 2 cache. They share the same PS UARTs, so that's the UART on the ARM processor, UART 0, global timer, I/O peripherals, on-chip memory, interrupt control, and external memory. But for the purposes of today's demo, we're not going to be using most of the stuff. So, just a little visual guide. We're going to give switches 0 and 1 to CPU 0, and LEDs 0 and 1 as well. And vice versa, CPU 1 gets these two switches and these two LEDs. So when we flip the switches on CPU 0, these two, we should expect to see these LEDs come on. And on CPU 1 side, when we flip these switches, we should see these LEDs come on. So go ahead and hop into Vivado. I've already gone ahead and created our diagram for today, and it generated a bit stream. So again, we have our two AXI GPIOs. Channel 1 for both of them is going to be the switches. Channel 2 is going to be the LEDs. So let's go ahead and export the hardware and launch SDK. While that's coming up, go through this flowchart real quick. So we're going to be doing two things with the shared memory today, or the on-chip memory, OCM, as you might see it referred to in the Xilinx manuals. So in order to write to shared memory, we have our pointer pointing to the shared memory address, and we can just set that pointer value. This changes it in our local cache, our level 1 cache, and then in order to get it to shared memory, we have to flush that cache. So that writes back the contents of the cache to the shared memory, so that the other CPU can access it. And we do a pretty similar thing on the other side, reading from shared memory. We have our pointer pointing to the memory address we want to read from, and before we read that pointer value, we want to invalidate the address that pointer corresponds to. So invalidating the cache forces the CPU to read from the main memory as opposed to the cache. Pretty straightforward. And as for the applications we're going to be writing, we're going to be doing two of these, one for each CPU. So the first thing we're going to do is, of course, initialize our GPIO, set up our shared memory pointers, and then in our super loop, we're going to read the switch values, check if it's the CPU's turn to access memory. So if the flag is a 0, so we're going to designate one address in the shared memory as a flag. And if that flag is a 0, then it's CPU 0's turn to write to shared memory. If it's a 1, it's going to be CPU 1's turn. Pretty straightforward. And then if it is said CPU's turn, then we write the switch value to shared memory, read the other CPU's switch value from the shared memory, set the memory flag back to, like if it's CPU 1, then we set it to 0, then vice versa, and set the LEDs. So pretty important note here. Only CPU 0 can set the flag to 1, and only CPU 1 will set the flag to 0. So that makes sure that guarantees that the CPUs don't try and write to the memory at the same time. Yep. Alright, so now that we're in SDK, we're going to go ahead and create two application projects, one for CPU 0 and one for CPU 1. We're going to use standalone OS. We're writing Baremetal applications here and targeting CPU 0, of course. And do another one for CPU 1. And make sure to set this processor to CPU 1. Just gonna wait for this to finish up. Alright, so the first thing we're going to do before writing any code is we're going to edit the linker scripts for both applications. So what we're doing here is we're allocating what memory regions each CPU is going to use as its cache. So yeah, CPU 0 is going to get a few megabytes. And CPU 1 is going to pick off right where CPU 0's ends, and we're going to get a few megabytes as well. And just so you can see, we do not want these to overlap. Alright, now we're ready to start writing code. Zoink that out of here. Alright, so first order of business, we're going to do a quick little sanity check. We're going to write like a little description. So this application programs CPU0 to check for the shared memory flag set by CPU1. If the flag is set to 0, then CPU0 shall write the value of 2 board switches to shared memory, read back the value of CPU1's switches from shared memory, and set its accordingly, its LEDs accordingly. And we're just going to do a little hello world. Or let's just CPU0 initialized. I guess it doesn't like that spelling. And the squiggly lines here. Alright, so we have our serial terminal here. Go ahead and launch that hardware. And we have CPU0 initialized, so that's good to go. We're going to do the same thing for CPU1, and then we're going to try and run them at the same time. And do the same thing. CPU1 initialized, looking good. Now we're going to try and run them at the same time. So I'm just going to have this program the FPGA just for convenience. You don't get that done pin not high thing again. The main thing we want to do here is we want to make sure we're programming both processors with the correct applications. And for CPU1, we don't want it to reset the processor when it gets programmed. So we're going to run that, and hopefully we get CPU0 and CPU1 initialized here. There we go. Alright, we're good to start writing code. Alright, what's the first order of business? Well, we need to set up GPIO, we need to set up shared memory, and let's write functions to handle the memory flag. So if we're using GPIOs, we need xparameters.h. That's the header file generated by Volatile that goes along with your hardware description file or your BSP, depending on whether you're using Vitis or SDK. We're going to need xGPIO, and we're going to use the sleep function later down the line. And we're also going to use zal_cache. This contains a bunch of pretty helpful functions that we're going to use to flush in and validate our cache. Alright, I'm just going to make some dividers here. Alright, our next step is to define whatever constants we're going to need. So I'll start with shared memory flag, shared memory CPU 0 data, shared memory CPU 1 data. So you recall when we allocated the memory for each CPU, our CPU 1 memory ends at this address. So let's just go ahead and make the flag the first address after that. And then this is definitely more space than's needed for the switches, for switch values, but looks pretty clean. And then we're going to do functions to set the flag and get the value of the flag, because that's something we're going to be doing quite a bit. So again, we're only designating a single address as the memory flag, or the flag status flag, I guess, whatever you want to call it. Again, if it's a 0, it's CPU 0's turn to write to memory. If it's a 1, it's CPU 1's turn. And we're going to do a void function, set mem flag. Value. These are 32-bit pointers pointing to, or that have that point to the address of wherever the flag is going to be. And the reason why these are 32-bit pointers is because our ARM processors are 32-bit processors. Alright, what is next? Set up the GPIO, set up the shared memory. Actually, while we're here, let's just go ahead and do our functions first. So we have get mem flag, and it gets the pointer to the flag address. So again, if we're reading from shared memory, we invalidate the lines of cache corresponding to that address, and then we can read it. So we're going to do that with this handy dandy function, zal_dcache invalidate range. And we're going to typecast our flag address as a 32-bit unsigned integer, and we're going to invalidate one line from there. And then we return the value of that address. Next we have our set mem flag. So again, going back to the flowchart, we are going to write to shared memory this time. So we set the pointer value and then flush the cache. So we are going to write the pointer value equals flag value, and then we flush the cache. Again, typecast our memory address as an unsigned 32-bit integer, and flush one line of cache, one address of cache, 1 byte. Alright, now we can write our main code. So we're using a GPIO for switches and LEDs, so 0 X Gpio. We're going to need integer to store our switch value. We need integer to store our the value that we read from CPU1. So CPU1 switch value. We're going to need a variable to store our shared memory flag status. And we're going to declare some volatile pointers pointing to our shared memory. So it's pretty important that these are volatile pointers. What the volatile keyword does is it lets the compiler know that even if the pointer does not change, or the value of the pointer does not change in this application specifically, it could be changed by another source. So it could be changed by CPU1, the flag, the data, and I believe it forces a memory read each time you access it. So now we're gonna set up Gpio 0, and then we're gonna set up shared memory. And since this is CPU 0, it's going to be initialized before CPU 1. We're also going to initialize the memory flag to 0. Initialize the shared memory data addresses to 0. So to set up Gpio 0, we're just going to use this xGpio initialize, pass it the Gpio object, and give it our Gpio, or give it our Gpio device ID. Next thing to do with Gpio is to set the data direction. So if you recall, our channel 0 is going to be, or channel 1 is going to be for the switches, so that's going to be all inputs. 1 looks like an eye, so that's an input. And channel 2 is going to be the LEDs, so 0 looks like an output, that's going to be all outputs. Alright, now we have to make our pointers point to our shared memory addresses. So let's typecast these just to be safe. Shared mem flag what you complaining about? Oh. I think I like CPU 0 data. I like this name better. Alright, and then we're going to initialize our memory flag to 0. So to do that, we can use our handy dandy function, set mem flag, and we're going to give it a pointer to our memory flag address, set that to 0. And then, since this is the first, let's just print it out on startup. Shared mem status equals right, now we're gonna write to the shared memory addresses for the first time. So again, we're just gonna set the value and then flush the cache. So shared mem equals 0. flush the cache in between each one. Now we're ready to write our super loop. Okay, so the first thing we're going to do in our super loop is we're going to get our switch inputs, we're going to read the shared memory flag, and then we're going to do stuff if the memory flag indicates that it's our CPU's turn to do stuff with the shared memory. Write to it, do all that. And after we're done doing the writing, we set the memory flag to allow the other CPU to access the shared memory. So first thing we're going to do is read switch values. Then we're going to access shared memory, if applicable, that is, and then we're going to set LEDs. So in order to read the switch values, we can just use X Gpio or discrete read. Read channel 1. Now we're going to access shared memory, so shared mem status equals, we can just use this. If the shared mem status equals 0, I guess you could just do if not shared mem status readability. And within this, we're going to read the switch values of CPU1. We're going to write CPU0 switch values to shared memory. You know, a fun little drinking game you can do is, you know, take a drink every time I say shared memory. I'm sure you have a lot of fun. Be on the floor by the time this is done. Set the flag based on CPU1. Oh, set the flag to allow CPU1 to write to shared memory. Check. Write, read, wrong order, it's okay. Set. Yep. So to read the switch values, again, the first thing we have to do is invalidate the cache. We're going to cast this as an unsigned integer. For 4 addresses, because the 32-bit value, even though we aren't actually using all 32 bits. What did we call this? We called it CPU1 switch value. CPU1 switch value equals next we're going to write our CPU0 switch values to shared memory, so we just go ahead and set that value, or it's actually CPU0 data equals switch value, and then we flush to the main memory, or the shared memory, by using this. That's it. And then we're going to set the flag to CPU1 to 1. So we give this a pointer. And we set it to 1. Next we set our LEDs. Last but not least, discrete write. channel 2, CPU 1 switch value. And, you know, while we're here, let's just print out the CPU 1 switch values as well. And since we're writing to the switch value, and we're printing the switch value, let's just sleep for like 0.1 seconds, just so it's a little more readable in the serial terminal. Alright, so we set up our GPIO, we set up our shared memory, we initialized all our shared memory. If the shared memory flag is 0, then we're going to get the CPU 1 switch values from the shared memory, print it out, write the CPU 0 switch values to shared memory, and then set the flag to 1. Then we're going to set our LEDs and sleep for 0.1 seconds. Alright, looking good. So I'm actually going to reuse a ton of code here. You know, what could possibly go wrong? For these set memory flag, get memory flag functions, this is actually not a very good practice to just have these here, especially since I'm using them again. I'm reusing them in this other application. This demo is kind of quick and dirty, but I would recommend doing it in a separate file. So pretty much it's going to be exactly the same thing, except we're not going to initialize the memory on CPU 1, and we are also going to sleep for maybe half a second at the start, just to allow CPU 0 the time to initialize the shared memory. Alright, and then we're not going to do any of that. Let's just rip this super loop. This is really important to change, because we only CPU 1 only writes if the flag is 1, and we also set the flag back to 0 as opposed to 1. Alright, let's go through this, make sure I didn't miss anything very dumb. I already found something. Alright, so we have our variables, we have our CPU1 x GPIO, which is set to GPIO1 device ID, or corresponds to this device ID. We have our switch value, we have our CPU0 switch value, and we have our memory flag status. We have our volatile pointers pointing to shared memory. We're setting up our X-Gpio. That is the correct GPIO. We assign our shared memory addresses to pointers. We're reading our switches from CPU 1. We're checking the flag to see if CPU 1 can write. If it's a 1, then we write. That's good. Read the switch values of CPU 0 from shared memory. That's CPU 0 data. That's CPU 0 switch value. And then we write the CPU 1 switch values to shared memory. So that's looking good. Set the flag to allow CPU 0 to write to shared memory. Yes, sir. Alright, it's looking good. Again, make sure everything is in order. Clear the serial terminal. I'm going to reset the board. Alright, so you can see CPU 0 and CPU 1 are alternating. This print statement only happens within this if statement here. So if it only prints if it's able to access or write to the shared memory. So that's all looking good. Let me go ahead and show you the board. So you can see that little orange light that's blinking every time we have a UART transaction. And now if I flip these two switches on your left, you should see the LEDs on your right light up, and vice versa. So there we go. You can see the switch value for CPU 1 changed in the serial terminal. And do the other switch. Both LEDs are on. Let's do the same thing for CPU 0. All the LEDs are on now. Now let's turn them off. Yep. Alright, I hope this has been helpful. Don't hesitate to leave a comment if I explained something wrong or you're having trouble getting this to work. Again, this isn't necessarily the best practice. You probably don't want to do it exactly this way for like a big project. But yeah, I hope it taught you a little bit, found it useful. Alright, I'll see you next time.